Hi everybody, welcome back to another video lecture. Today we're just going to be going over some little pieces of information that we want to add to this idea of Lewis dot structures and kind of help explain how do these bonds form, why does the bond strength important, and how do the length of the bonds affect the strength of the bonds. So on this slide here, we need to learn two new terms. We need to learn sigma, and this is the little symbol for sigma, and pi, and of course you guys have seen the little symbol for pi before. So scientists will classify specific bonds as being sigma bonds and pi bonds, and you will need to do that too. So the first thing that we need to do is a sigma bond is where you have electron density is concentrated about the line connecting the nuclei. So this little thing right here, where I'm kind of moving my arrow here, is called the internuclear axes, okay? So hopefully from that video, you remember from the covalent bonding tutorial, we saw that those electrons were bonding or being pulled by this nucleus and this nucleus, and so they were going back and forth here. So the idea is that this one is called a sigma bond because it's between the nuclei of the two atoms. On the other hand, you might have what we call pi bonds, okay? And this is where you have a bond, but because we already have a bond here from the sigma bond, they're going to be bonding or moving back and forth or have high electron density above that internuclear axis and below that internuclear axis, okay? So notice that in this picture, there would be a sigma bond here. We're just not showing it in this picture. But if the electrons are bonding up here, we're going to call this a pi bond, and then this one we're going to call a pi bond. So what we want to do is if we were just looking at a simple picture, so if we just see carbon here, we would just say that this has one sigma bond. So you guys with me? This is a single bond. So anytime you just have a single bond, we're going to say it just has one sigma bond. On the other hand, if I had a double bond, we would say that one of these would be the sigma bond, and it doesn't really matter which one you choose, and then the other one would be the pi bond. Okay, so this, in this category, I'm just saying like this is the one that's going between the two nuclei. This is one is going above or below that nuclei because remember the electrons repel each other. And then in a triple bond, oops, I just kind of did that in a different color, but whatever, you guys get the idea. We would say that there's one sigma bond. Hopefully you guys can see I'm pointing to that middle bond. That's how we'd usually describe that as being the sigma bond. And then the one above and below would be these pi bonds here. Now take a second, look at these structures. These are from the Lewis dot structures we did before when we were talking about double and triple bonds. And just for yourself, like go through and be like, okay, this structure has one sigma bond, one pi bond. And I don't mean the individual bonds, like look at the overall Lewis structure and count them up. Just pause the video and then push play so you can see what the answers were. So as we look at these structures here, in oxygen, we just had to worry about the single double bond, so that we're going to have one sigma and one pi bond here. Over here, we've got the triple bond, which we saw in the last slide. So again, we're going to have one sigma bond and two pi bonds here. Now, if we look down here at carbon dioxide, we'd actually say that it has two sigma bonds because we'd say like this is a sigma bond, this is a sigma bond, and then notice that we have a double bond there. So that's why we're going to have two pi bonds here. And then over here, we'd have two sigma bonds, and then again, two pi bonds happening here. Now, hopefully you guys are remembering that that chart that we looked at where we had the potential energy on this side and we had the bond length on this side, and the chart kind of looked like this, and down here was like where the atoms found their perfect bond length. Okay, so the way that we measure bond length is in this term, and I don't know why I just love saying it, picometers. It just sounds so much fun. So picometers is the unit that we use to measure bond length. What I want you guys to get out of this slide is the larger the atom, the longer the bond. So if you were to look on the periodic table, hopefully you're thinking, okay, we've got carbon is bigger than nitrogen. And that's because nitrogen has more protons to pull that valence shell in. So we would see that the size of the atom will help determine the bond length. And in this case, carbon has a larger bond length than nitrogen does because carbon is a larger atom. Then we also need to know that as we have more bonds, the shorter the bond length is going to be. So in this case, if you guys have a triple bond, it's going to be the smallest bond. Because you have those so many electrons pulling the nuclei closer to each other. Then over here we've got a double bond, so that's kind of in the middle, and a single bond would be the longest. And sometimes I like to make an analogy, like if you were just holding like a single hand with a partner, you could be pretty far apart, but if you were holding two hands, you would be closer to your partner. So that's why we'd say that a double bond is a smaller bond or a shorter bond than a single bond would be. There's that more attraction going on there. And you guys, this is the last slide in this video. We just need to talk about bond strength and bond energy. So this is going to be related to the last slide when we were talking about bond length. So when we say bond strength, okay, we're talking about like how strong that bond is. And then one of the ways that we know the strength of the bond is we can measure the amount of energy that's released when the bond is broken. Sorry, when the bond is formed, or we can measure the amount of energy that's needed to form that bond. And so again, we're going to see here it says generally the shorter the bond, the stronger the bond will be. And I give you a little definition here. It's described as the amount of energy required to break that bond. The more energy required, the stronger the bond. And then down here, we have some examples. So we have hydrogen and chlorine, hydrogen, bromine. We know that bromine's the larger atom here, so you can see that it requires less energy. And then when we look at our double and triple bonds, again, shorter the bond, more energy required. Longer the bond, less energy required. And again, I have a silly analogy here. Hopefully you guys have played with silly putty before. If you pull silly putty a little bit apart from each other, like say you've got your like silly putty, I don't know, it's kind of this an awful picture. So you've got silly putty here. But if you were to pull it apart like really long, okay, this one's going to require like a lot of energy to pull it apart, whereas if your silly putty, I don't know, these pictures look weird, but if the silly putty is pulled far apart, it's a less energy. So that's the same idea with bonds. Further apart, less energy. Closer together, more energy is required. Okay, guys, I hope you guys took your notes. Please write down any questions you have and ask me in class. Thank you.